So here we have 5.1 lesson. So we have a reaction between acetic acid and sodium hydroxide. We know that that's a strong base and all the hydroxides will come off. And for the purposes of pH and so forth that we're going to be figuring later on, we can ignore the Na plus, can't we? So here's the net ionic equation. And so let's go on to part B. If we had this much of the acetic acid and this much of sodium hydroxide, what we've got is an acid. It's not a strong acid, but it does have an H on offer, and that is a very strong base. That OH minus is a real acid chewer. So when we do liters times molarity and get moles, and liters times molarity and get moles, what we've got then is this reaction. Let's write it out again. We started with this amount of moles, don't we? This is the amount of moles for this, and this is the amount of moles for the hydroxide. And one of these will chew up one of those. And they make the point down here that when one of them is strong, in this case the base is strong, we can consider that the neutralization reaction goes to completion. We don't need to fuss around with K or something and say, well, what portion of the OH minuses will react? The answer is all of them. Let's just use all of them. For all practical purposes, it's all of them. So 0.03 of these will chew up and react with 0.03 of those, which is why that's the amount disappearing here. So this amount will use up the same amount of this chemical, which means that they're all gone because we used them up making these. Now, I don't care about the molarity of water and the moles of water, so let's just put an X there. But when I have effectively, let's just put the decimal here for a minute. If I have 4 of these and 3 of these, then 3 of these uses up 3 of those and leaves me 1 of those. That's the kind of ratio I'm talking about. Now, this is all gone, so I have 0 of this. And one of these reacting with one of those makes one of these. So it generates the equal amount of moles there. So this is the amount I have at the end of my strong base, weak acid reaction. Now, here's a wrong idea that I went on at some length in a class. Um, and they make the point that this is not the final reaction mixture because the buffer solution needs to go to equilibrium. And that's true. I mean, what are the odds that we happen to generate just the right amount to set up an equilibrium right there, dead on? I mean, it's pretty poor. So this is probably not true that Q equals K, and this is probably not the final exact amount that you will settle it will settle for equilibrium. However, you can't just take this amount and put it to the first power and over this amount to the first power and get Q. Now, another little point that will come up is I'm going to point out Q is dependent on molarity. And so if we're going to do this, we're going to try to use molarity, we got to divide by the new 70 milliliters, 30 and 40 milliliters, which is 0.07 liters. But I had to do it in both places. And since I'm using a fraction over a fraction, the bottoms of each fraction will cancel out. So when you have one of these reactions and you need molarity, but they're both in the same beaker like this, then you can just disregard the liters because it would have canceled out anyway. You don't even need to go find out what it would have been because it would cancel out. Then we can have the E negative 3 will also cancel out and I just get 3. However, this is not Q in reality because this is not the reaction on offer anymore. What we've set up is, remember, we lost all the OH minus. What we got now is this. I've got some of this and some of this in water. And what happens when you have that? Well, some of the HAC acts as an acid and it makes more of that, right? And it makes H plus. But I already have some of this, you say. Yes, we do. So we started with this, we started with that, and I got these numbers from here. Some of this will get destroyed, making some more of this. And some of this will get generated, the same amount. So I'll lose a little bit. That same amount will get added here, and that same amount will get added here. But if this started effectively at 0, because I'm only dealing with the amount that I had from water, from the natural dissociation of water, and I don't really care about that number because it's so small, so I'm going to call that 0. So this is my equilibrium numbers, and then I can put this in to Ka. In with Ka, and products over reactants to the power of the number in front, and this is Ka because I looked farther down the page, and this is the Ka for acetic acid. Here's the thing though, I can cross out plus x and minus x because Ka is 3 decimals or more smaller than the molarities at hand. And so do these numbers change? I just said they didn't. I just said the change in them is immaterial mathematically. Let's ignore it. Well, then how can it shift? How can it achieve equilibrium if these don't change and Q is not K probably, right? The answer is because it's going to generate some H plus or hydronium H3O plus if you like. And this amount is going to come up from being 0, and it's not going to be a big number, but it's going to be the proper number that when we multiply this fraction, this decimal, small decimal, times this, and divide by that, we do get K. K is a law of nature, and when you get an equilibrium, K is true. So you give this stuff, and this is done, you give it a shake and so forth, and you will set an equilibrium, set up an equilibrium, but not by changing this so much, but by generating enough H plus that this mathematically is small enough that multiplied by this, divided by this, will generate K. That's going to come up again on 2b, by the way. So what was the limiting reactant? Well, it's this one because it ran out, didn't it? And this is a buffer solution. We have a weak acid and the conjugate base, or we have a weak base and the conjugate acid. Either way you want to define it, it doesn't really matter. And the point of a buffer system is that the pH is kind of hard to push around because if you put in some acid, you've got some base to react with it. You put in some base, you've got some acid to react with it. And so the pH doesn't just yo-yo up and down like it would in sort of a normal situation or a normal solution. And that's the point of a buffer, is it's pH movement resistant. Now, for example 2, let's talk about this amount, the molarity of sodium hydroxide and this amount of molarity acetic acid. But for part A, no NaOH has been added. Okay, so let's just deal with it with no NaOH. We just have this acetic acid. And in that case, what matters is the molarity. If we're not going to deal with a reaction with another chemical and we're just going to deal with the acid nature of the acetic acid, then I don't need to know the amount. I just need to know the molarity. So this is going to start off at 0.1. We have none of this and none of this. We lose some, we gain exactly the same amounts. We lost this and we gained that. So Ka is 1.8 e negative 5, and it's equal to products over reactants, all to the first power, except that Ka is small enough I can cross out x, and we generate x, which is H plus. Notice it's H plus, and I wanted pH, right? Find the pH of the solution. So I can take negative log of that and get pH. Now, I also want to talk about some mental math here because I can take a pretty good whack at finding this answer, and I don't even have to use a pencil. Once I set this up, I'm going to multiply by 0.10. Well, where does the where does the exponent move when I multiply by 0.10? When I multiply by 0.1, the number has to get smaller. So does this exponent go to negative 4 or negative 6? Well, negative 6 is smaller. So this is now 1.8 e negative 6 when I move this over. And then I had to take the square root to find x. And I find out a lot of kids have not been taught this part. Ignore these numbers just for a moment. Let's pretend they're not there. When we multiply numbers of a common base, we add their exponents. So to find the square root of 1 e negative 6, and somebody's shouting, it's not 1. I'm just going to do the e number first. What if it was 1 e negative 6? What would it be? What would the square root be? I need two numbers that are identical, and the exponents on the common 10, the exponents must add to negative 6. What's in the box? What's the exponent in the box? And they must be the same. It must be negative 3 as the exponent. So square root of 1 e negative 6 is 1 e negative 3, or 10 to the negative third, same thing. So square root of this part now is 10 to the minus third. And this is almost 2, and square root of 2 is 1.4. So this is a little bit lower. It's kind of like maybe 1.3. Ding. It's 1.3 e negative 3. Now, the other thing to watch out for, and they really do this on the test occasionally, is they set you up so you need to write it out as an acid equation, or they've written it out as an acid equation, but what they've handed you is Kb, or they've written the base and you need Ka. Now, we need Ka for this, right? Just pretend they had given us Kb just to be difficult. This is how we would generate Ka, because this times this must generate, this is Kw. This is the K for water. Now on part B, let's add 10 milliliters of NaOH. Okay, so all the OHs come off, and that's the part I care about. So let's get the moles, not the molarity, for both reactants, because this is what we've got going on now then, right? Take a look at that. Liters times molarity is moles and moles, and so that's where I got these numbers. This means millimoles, which means 10 to the negative 3. So this isn't 4, it's 4e negative 3, or also called millimoles, because milli means 1,000th. So what happens? Well, again, one of these will burn up one of those. So if I have one of these, it burns up one of those. That's where this, why I'm subtracting this out. That's where that went. And that's what gives me 3. This is all used up, and this started at 0. So I end up with 1 e negative 3, to be picky, moles of the anion. The water is immaterial. Let's cross that out. Now we have a buffer solution again. We have a weak acid and the conjugate base. What is the pH? Now, there are two ways to do this, one of which is the Henderson-Hasselbalch reaction, which I recommend you memorize. It is in the booklet, but that kid who gets a 5 is going to know this. The difficult part for me was always remembering which one was on top, the base or the acid. And I finally decided this looks like a pyramid, and now I know which one it is. It's kind of a dumb method, but now I remember that my smaller one, the A minus, goes on top. So we said, remember that the Ka for this acid is so small that we can essentially say that this amount in this amount are not going to change. What's going to happen to the moles of those? Essentially nothing. Now, this is molarity, see the brackets. And I technically, to be super picky, have to divide each of these, because this is moles, by the milliliters, which is 10 and 40. So I have to divide by 0.05 liters, divide by 0.05 liters, but that's going to cancel out. So there's no point in it. Because they're in the same beaker, when I've got a fraction like this, it's just going to cancel out. I don't even have to go look and find out what the liters would be. I know they're going to cancel out. Dividing by liters to get molarity will just cancel out in this case, because I'm going to use them directly over each other, and there's no plus x or minus x and anything like that. So there's mathematically no point. So what I need is pKa. P number is the negative log of the number under discussion. So the negative log of the Ka got me that. Log of 1/3 is, I forget, some amount, add them together, and they equal pH. Now, I went and did it another way, just to kind of prove that you could. We now know that since this is gone, as I said back up on example 1, that what I've got is this going on. And I wrote it out this time the more official way, with the hydronium being generated in the water as a reactant. So we know that really the moles are in 50 milliliters of water, right? Or 0.05 liters and 0.05 liters. And so this is the molarity and this is the molarity, really. So K will be equal, Ka, because this is an acid reaction, Ka will be equal to products over reactants to the power of the number in front, except remember, this is going to be losing some amount. This is going to be gaining some amount, and that's where I got these. Except we said Ka is so small that plus x and minus x doesn't really matter, so we can cross them out. So when I take this, also reduces to 1/3, and when I divide by 1/3, I get this, and that is x, and x is H plus, or H3O plus, and negative log of that will give me pH. So you can do it either way. Also, I will point out, again, because these are in the same beaker and it's just a simple ratio like this, because we're going to cross out the x and minus x, the plus x and minus x, I could have skipped this part because I could have said 3 over 1, and look, that boils down to 3 over 1. Excuse me, it would be 1 over 3. 1 over 3, and this is 1 over 3 essentially. So I don't really have to divide by the liters. I could have just skipped ahead with the moles in this case, because I'd be dividing by the same number in both the numerator and the denominator of this fraction. I went then and also solved it as a base, just to prove to myself that we could do that. I said, you know what? There's no reason to assume automatically that this is an acid reaction now, right? Because I've got some of the base and some of the acid. So I turned it around and I went and solving it. Here's my moles, and here's my moles. This is millimoles, I guess, if you want to be picky, and millimoles. And I had to go get KB, so I did that by dividing it into KW. Now I have KB, and I have my products over reactants, the power of the number in front, except I'm going to be gaining on this one and losing X amount on this one. But you know what? It's immaterial. Let's cross those out. So we get 3 times X. So I divide by 3. Here I get 3X, divide by 3, and I get X. But what is X? X is the OH minus. So I took negative log of that answer. And I get POH, and 14 minus that answer is 4.27. So close as to be essentially the same thing. You can solve it this way too.